Yeah, so last time we didn't finish Lagrangian relaxation and decomposition. I remember we stopped at the subgradient method, right? But just to refresh your memories, when we are doing Lagrangian relaxation, we dualize those complicating constraints, right? But then the question is, how do you solve this Lagrangian relaxation problem, right? You want to maximize the dual function. Then there are two different methods we talk about that maximize the dual function. One is the so-called cutting plane method, right? You write out the dual explicitly as the minimum over all the extreme points, but you don't want to enumerate all the extreme points. Then what you do is that each time you find the maximum violation of the cuts in the Lagrangian master problem, in order to do that, you solve something like a Lagrangian subproblem, right? So the Lagrangian subproblem is very similar to the pricing problem in Danzig-Wolff decomposition. Actually, you can prove they are exactly identical. And also, you can prove that the Lagrangian master problem is a LP dual of the Danzig-Wolff master problem. We will leave this as a homework question. So the second method we talk about is the so-called subgradient method. Right? The idea of the subgradient, we show the definition of the subgradient. The idea is basically very similar to gradient descent or gradient ascent. Here you are doing a subgradient descent, right? And we show that at any given point lambda naught, the ax naught minus b is a subgradient. Okay, so that's what we want to talk about for Lagrangian relaxation. Yeah. So then we will talk about something called Lagrangian decomposition. Yeah, so Lagrangian decomposition is nothing but a reformulation of the original problem. Right? So here, let's assume you have two sets of the constraints, the complicating constraints and the non-complicating constraints. In Lagrangian relaxation, we just dualized this constraint here, right? But now let's suppose that these two constraints are both quite complicated, right? Without loss of generality, you just assume these two sets of constraints are equally complicated. Okay, so what you can do is reformulate the problem as follows. You create a new variable y, and then you put x to satisfy the first set of linear constraints and y to satisfy the second set of linear constraints. But then, this x can be a set of mixed integer variables, and you put x into capital X, and y has to be mixed integer as well. But then we need to make sure that x equals to y, because y is like a duplication of the original x variable. You just want to duplicate the variables and then make them satisfy the two sets of constraints respectively. Right. Okay, so with that, I hope everyone is clear that these two problems are equivalent to each other. Right? You just duplicate a variable and then you add a simple constraint saying x equals to y. So in order to apply Lagrangian, one way you can do that is dualizing x equals to y. Right? So now the x equals to y are like the complicating constraints in this problem. Right? Once you remove these constraints, then x are separated from y. You can solve these two problems separately. So let's say if we dualize x equals to y by multiplying this, let's say the Lagrangian multiplier is called nu. Then you can separate the original problem into two subproblems. One corresponds to the x variables, the other corresponds to the y variables, right? Then you solve these two Lagrangian subproblems separately. Okay. And the dual bound, by definition, would be the maximum of the over the Lagrangian multiplier, and then you sum these two problems up, right? So here, a naive question to ask is, now what we did is that we did a very simple reformulation of the original problem, then we create different types of Lagrangian dual, right? So how does this Lagrangian dual let's call this problem the Lagrangian decomposition or dual decomposition. How does this bound compare with the bound of the Lagrangian relaxation? Right? So recall that the difference between the Lagrangian decomposition and the Lagrangian relaxation is the following. Right? In the Lagrangian relaxation, we just dualize these constraints, right? Ax less than or equal to b. But in Lagrangian decomposition here, we duplicate the x variable, right? And then we have to create a new set of complicating constraints. It is very trivial, it's x equals to 1. But then instead of dualizing this constraint ax less than or equal to b, we dualize x equals to 1, right? That's the main difference of these two problems. Okay, so now we are wondering that does Lagrangian decomposition give you a tighter bound than the Lagrangian relaxation? Actually, this is true. We will show that in a second. But then before we show that mathematically, maybe we can think a little bit about the intuition why this can be true. So recall that in the Lagrangian relaxation, right? What is the Lagrangian subproblem we are solving? Okay, so let's go back a little bit. All right, so this is called the, where is it? Yeah, so this is called the Lagrangian subproblem we are solving for Lagrangian relaxation, right? So it involves a linear function of x, and the constraints are ex less than or equal to d and x being mixed integer. Right? That's a single Lagrangian subproblem we are solving in Lagrangian relaxation. Okay, now let's go to Lagrangian decomposition. So those two problems are the Lagrangian subproblem we are solving, right? So the second problem is exactly a linear function over the constraint ey less than or equal to d, y is mixed integer, right? But then in addition to this problem, we are also solving a problem to be ax less than or equal to b, x is mixed integer, right? So as you can see that in Lagrangian decomposition, at each iteration, it's more expensive than the Lagrangian relaxation, right? Because we are solving two problems, and one of the problem has exactly the same computation complexity as Lagrangian relaxation, right? So you are solving a more expensive Lagrangian subproblem, okay? And then even if you don't know this proposition, I would guess that Lagrangian decomposition should give you a tighter bound, right? Otherwise, it's not worth doing that. You are solving something more expensive, okay? And if you are solving something more expensive and it's even worse, then this algorithm is not worth doing at all, right? So when you are doing your research, it's a good practice to make some guesses on whether something is true or not before you prove that, right? Because when you read the papers, all the mathematical papers are written in a backward fashion, actually, right? The mathematicians have already made some guesses, then they go to prove that. You are seeing the results of their proofs, but you don't know how they came up with those conjectures, right? So when you are doing your research, it's a good practice to make some conjectures before you go to prove something, right? So that's why I say, in the research of math, usually all the papers are backwards. If you read the papers, you don't get any intuitions how they did that at all, right? They may have tried 100 different things, but only one thing works at the end. But they didn't tell you whether, how the 99 other different ways feel, okay? Yeah, so let's prove this proposition, right? So we can prove that using the primal characterization. Remember that when we are doing Lagrangian relaxation, we prove this theorem. The bound of Lagrangian relaxation is the following. It is an objective subject to the, the constraints you dualize, intersect with the convex hull of the constraints, you did not dualize, right? That's a theorem we proved before. And then we can apply this theorem to Lagrangian decomposition, right? So Lagrangian decomposition is a special case of Lagrangian relaxation. The difference is that the constraints you dualize is x equals to y instead of ax less than or equal to b, right? So ax less than or equal to b can represent any arbitrary constraints. So now you can treat your constraints as x equals to y, right? So then if you apply this theorem, okay, recall that the primal characterization is the intersection of two sets, right? The first set is the complicating constraints you dualize, right? So now you are working in the domain of both x and y variable instead of just the x variables. So the first set is this complicating constraint you intersect, you dualize, and then you have to intersect with the constraints you did not dualize, right? So what are the constraints you did not dualize in the Lagrangian decomposition? That would include the set of constraints you solved in the Lagrangian subproblem, right? So those are the constraints related to x and constraints related to y and their convex hull. Okay. Now let's simplify this a little bit. Well, what is x equals to y intersected with the convex hull of this set? Okay. So first of all, you can realize that the x and y variable doesn't depend on each other in this set, right? Because once you dualize x equal to y, the two sets of constraints are separable already. But now if you intersect this set with x equals to y, that is equivalent to you take the convex hull of the constraints equals to x and the convex hull of the constraints equals to y respectively. But since x equal to y, you can just write them as both with respect to variable x, right? And then that will simplify to this set. The convex hull of ax less than or equal to bx being mixed integer intersect with ex less than or equal to dx being mixed integer. Okay, so now we can compare apples with apples, right? Originally, in the Lagrangian decomposition, you have both x and y variables, but with this simplification, we only have the x variables here, and then in the Lagrangian relaxation, we also only have the x variables. Okay, so let's compare these two sets. First of all, it's easy to recognize that this part and this part are exactly the same, right? Then we only need to compare these two sets, right? This one and this one, right? Which set is bigger, which set is smaller. And it's very clear that the convex hull of ax less than or equal to bx is mixed integer is contained in ax less than or equal to b, right? Because the first set is more constrained than the second one. You have a mixed integer constraint in the first set. Okay, so then it is easy to show that the Lagrangian decomposition must be greater than the Lagrangian relaxation because this set, this feasible region is more constrained in Lagrangian decomposition. Okay. Yeah. So now let's show a geometric intuition with this this picture. Then you will have a very intuitive view of primal characterization. All right. So first I'll recall that what is the linear programming relaxation? It is just the intersection of the LP relaxation of the two polyhedral set, right? The two big polyhedral set intersected at here. So of course the LP relaxation is the weakest relaxation, right? And the Lagrangian relaxation gave you the convex hull of the points in this region intersect with the linear constraints that you dualize. So the Lagrangian relaxation will be obtained at this point here. Okay. And the Lagrangian decomposition should be the intersection of the convex hull of the left side polyhedral and the convex hull of the integer points in the right polyhedral. Right? And then the intersection of the two convex hull will give you even tighter bounds than the Lagrangian relaxation. Okay, you can go back to the algebraic definition. It's just intersection of the first convex hull and the right-hand side convex hull. Right, so that's a Lagrangian decomposition, and the original problem solution has to be an integer point, which is this point here. So that shows you a kind of a hierarchy of bounds from LP relaxation, Lagrangian relaxation, Lagrangian decomposition to the original problem. Okay. Yeah, so another thing I would like to talk about real quick is how to obtain a feasible solution in Lagrangian decomposition. So far we only talk about how do you obtain a good bound, right? By solving the Lagrangian master problem or doing subgradient method, right? That only gave you a lower bound of the original problem. But when we are solving an optimization problem, we not only need a lower bound, we also need an upper bound, right? So the upper bound is a feasible solution to the original problem. So how do we obtain a feasible solution to the original problem from, let's say, Lagrangian decomposition? Yeah, so then that is actually the dark side of Lagrangian relaxation, because it doesn't really guarantee to give you the primal feasible solution or the primal optimal solution. You can only obtain a primal solution from some heuristics. So here's one of the common heuristics to use. So let's say you solve these two Lagrangian subproblems, right? Then you will get an, if you solve these two problems, denote the solution to the two subproblems, let's say as x naught and y naught, right? Let's suppose at a given iteration of the subproblem. So if x naught equals to y naught, what can you see about x naught and y naught here? Mm-hmm. So if you solve these two subproblems here, right? Let's suppose it happens to be the case that x naught equals to y naught. What can you see about x naught and y naught? It's feasible. Can you see it's also optimal? Right? Okay. Any other ideas here? Yeah, actually, yeah. You can write a simple proof that if, let's say x naught and y naught are the optimal solution to this problem, right? We have, let's say they are equal, then I will claim that are optimal to the original problem. Right. Okay, so let's show that real quick. Why I claim if you solve the two Lagrangian subproblem and x naught equals to y naught, they will be optimal to the original problem. Okay. So first of all, in order to show a solution is optimal, we need two things, right? One is they are feasible, as you guys just suggested, right? So first of all, they are feasible. Why is that? Because they satisfy all the primal constraints, right? So x naught satisfy this part of the constraint, y naught satisfy this part of the constraints, and then they are equal. They must satisfy all the constraints in the primal problem. So they are feasible. Okay, so how do we show they are optimal? Okay, and then we already show they are feasible, right? So since x naught equals to y naught, then this objective can be written as C transpose x naught, right? Because they are equal, right? So this is the, let's say, is an upper bound. Right, because they are feasible. A feasible solution to a minimization problem is an upper bound to the original problem. Okay, so can we also show that C transpose x naught is also a lower bound? Right, if we show C transpose x naught is also a lower bound, then it must be optimal. Right. Okay, so let's show that real quick. If you, we already know that for any given Lagrangian multiplier, the Lagrangian dual function is a lower bound, right? So we already know that dx mu plus dy mu is a lower bound for any Lagrangian multipliers, right? This is what we have been talking about this many times, right? Okay, so in this case, what is dx mu plus dy mu here? If x naught equals to y naught.
1/2 C transpose times x naught plus y naught. It's the original objective.
Yeah, it's just this, because if you add them up, if x naught equals to y naught, these two terms will be canceled out, right? If you add them up. So, and then they are equal, then, they're, if you add them up, they are nothing but, C transpose x naught, right? So we know that C transpose x naught is a feasible solution and it is also a lower bound. So that certifies that C transpose x naught is the optimal solution to the original problem. Yeah.
How do you know that the two subproblems have the same Lagrangian multipliers?
Yeah, so that's by definition, right? You are dualizing the constraint x equals to y. Right, so you multiply mu to the constraint x equals to y, right? So it's like you have a mu transpose x minus y in the dual.
Okay.
Right. Yeah. Yeah. That's why they cancel out. Okay. So in that case, what we have here is that if the x naught equals to y naught, then we can certify the optimality. But this usually doesn't happen in practice, right? Because if that happens, you got zero duality gap, right? For mixed integer programming problem, usually you don't get zero duality gap, actually. Okay. And then in most cases, we don't have x naught equals to y naught. Then what we can do is that to use a heuristic to find a feasible solution. For example, you can just take the average of x naught and y naught if they are fractional, right? Because you want to make them satisfy the integrality constraints. If you take their average, they may not satisfy the integrality constraint, right? Because x naught and y naught satisfy integrality constraint respectively. But if you take the average of them, they may not be satisfying all the integrality constraints. Then what we can do is we will round the fractional integer variables after you take the average. Let's say if we are, quote, lucky, then x bar would be a feasible solution to the original problem. The other commonly used heuristic is to check whether x naught and y naught themselves are feasible. Because when you solve the right-hand side problem, you are satisfying those constraints, but you may not satisfy ax less than or equal to b. Right? If you are lucky, maybe the optimal solution to the right-hand side problem also happen to satisfy ax less than or equal to b. Okay, yeah, those are the commonly used heuristics to get feasible solution, but there is no guarantee of convergence when the original problem is mixed integer. Any questions here? Okay. Yeah, so here's what I just said, right? Usually Lagrangian decomposition applied to MILP does not provide a zero gap. This is because of the primal characterization, right? We have the pictures shown before. And then usually in practice, what you can do is just run it for a few iterations. If if the upper and lower bounds don't improve, then you terminate with some optimality gap, right? If you are lucky, the problem may have good optimality gap. But then to guarantee convergence, you may need to do some branch and bound on the variables involved in the complicating constraints. We are not going to the details of that. You can check. There's a paper by Carreau and Schultz in 1999. And a similar property hold for Danzig-Wolff decomposition when the Danzig-Wolff subproblem are integer constraints. So we already showed that actually Danzig-Wolff and Lagrangian are just the LP duo of each other, right? So if the Danzig-Wolf is integer constraint, it also doesn't guarantee to converge. You need to do some branch and bound. So this is called something called branch and price in the literature, right? So when you do column generation, if the columns have to be integer constraints, but in the master problem, you are just doing convex combination of the columns, right? And the convex combination of those columns may not be integer anymore, right? Even if all the columns are integer constraint. So in that case, what we need to do is to branch on the integer variables in the Danzig-Wolf master problem. This can be shown. Maybe there are some connections with Carreau and Schultz. I don't know if someone has showed that or not. Okay, so that's all the references we have. I would recommend you can check this paper on Lagrangian relaxation. Everything I covered in the lecture is in this tutorial of Lagrangian relaxation, and then this paper is the paper that can guarantee convergence. All right, so then I will move to the next lecture. Are there any questions here? Okay. So then let's talk about something called Augmented Lagrangian and ADMM. So you can see these two methods as an extension to Lagrangian relaxation. Okay, so in Lagrangian decomposition or Lagrangian relaxation, we are focused on MILP problem. The reason is that we want to make it as general as possible, right? Even with MILP, you can show some properties, and then you can show some convergence properties. But the augmented Lagrangian and ADMM for MILP problems are not as mature. It is still a very active research area. So I will show you some reference at the very end of augmented Lagrangian and ADMM for MILP problem. You will find out the papers were published in the last 3 years also. So of course in a course we only talk about something that is mature rather than something is under active research. So that's why in this lecture, we will talk about augmented Lagrangian and ADMM for continuous and convex problems. Right? So those problems have very nice property. Then you can show those methods converge. Yeah, so first of all, let's do a very quick review of what we did in the last lecture. So when you apply Lagrangian relaxation to a continuous problem, right? So here we have a continuous function f of x subject to linear equality constraint. When you naively apply Lagrangian to this problem, it is called a dual ascent method, right? Of course, this method predates the methods we talked about in the previous lecture, right? In the previous lecture, we were talking about Lagrangian relaxation for MILP problem, and now we are talking about much easier problem, continuous convex problem. I just want to give this overview before we go to augmented Lagrangian. Okay. So first of all, you can, if you have this problem, you can define Lagrangian as fx plus y transpose ax minus b. This is nothing fancy, and the dual function is a function of the dual multiplier, but then you minimize x for each of the dual multiplier, and the dual problem is maximizing the Lagrangian dual function, right? So a dual ascent method is nothing but the subgradient method we talked about in the previous lecture, right? For each of the fixed Lagrangian multiplier, then you optimize for x, right? And then we show that this term is a subgradient, right? When the problem is an MILP, but when the problem is continuous convex, this is just a gradient of the dual function. Then you can just take the gradient in the dual. That's it, right? So this is nothing but subgradient method applying to a continuous problem. But actually, when the problem is continuous, it is a gradient, not a subgradient, right? It's just much easier than the problem we talked about in the previous lecture. Okay, so how to apply Lagrangian decomposition or dual decomposition into a continuous problem. Again, this is just a review of what we did before. For example, if x is decomposable, you have x that it can be represented as x1 all the way to x capital N, and all those functions are let's say they are decomposable, then what you can do is you can, let's assume the constraints are can be written as you just write it out as a summation over ai of xi in this particular form. Then you dualize this constraint. Then the rest of the problem will be separable after you dualize these complicating constraints. Then you can optimize each of these x in parallel, right? Because the functions are separable, and after you dualize the constraints, the rest of the problem will be separable. Okay. Yeah. So that's what I said. At each iteration, you can optimize for each of these xi separately. If you have a parallel computer, you can assign all those problems to a different threads of your computer. Then after those subproblems get solved, you collect all the xk plus 1 to update the dual multipliers. Okay, so this is a very old concept in optimization that dates back to the 1960s. You can use this to solve large-scale problems, right? So the idea is, you solve each of the subproblems separately, and then you collect the updates of the, this new iteration of the x variables. Then you use the gradient to update the dual variables. Okay. Yeah. So here's just a review of what we did in the previous lecture to the continuous problem. So what are the issues with dual decomposition or Lagrangian decomposition? The issue is that the convergence can be quite slow in dual decomposition. And the other thing is that with dual decomposition, you may not end up with a primal feasible solution, even if the problem is convex. So we showed that in the MILP case, you may not end up with a primal feasible solution, right? Recall that we just showed that if you have, maybe go back here. If you have x naught equals y naught, you end up with a primal feasible solution, and then it must be optimal, right? But this usually doesn't occur in practice, right? You may end up with x naught always not equal to y naught. And same thing here, even if you have a convex problem, since you dualize this constraint ax equals to b, right? You may not end up with an x that satisfies ax equals to b, even though the problem is convex. The reason is that even if you have strong duality, the solution to this Lagrangian may not be unique, right? So you may have an optimal solution that satisfies ax equals to b. But if this solution is not unique, you may have another solution that gives you the same objective value, but violate the constraint you dualized. Okay, so again, you are dualizing this constraint in the Lagrangian problem. Okay, so that's okay, so here you dualize ax minus b, right? And then when you are minimizing this problem, this constraint may not hold in this problem, right? So although you may get the same objective value as the optimal value of the original problem when strong duality hold, you may not end up with the same optimal solution, right? So my point is that different optimal solution can give you the same objective value. The optimizer may not return you the one that satisfies this constraint ax minus b since it has been dualized. Okay, yeah. This probably will be more clear if you try to implement this for a linear problem and see if it satisfies the primal constraint, although it converges to the optimal objective. Okay, so if you believe in that, then how do we resolve those issues of dual decomposition? How do we have a method that satisfies those primal constraints? So that's why people develop this augmented Lagrangian method. Okay, so what that means is that this is just the Lagrangian function, right? You have fx plus y transpose ax less than equal to b. You have the original function plus the Lagrangian term. But augmented Lagrangian is saying I'm going to augment this function by a penalty of the violation of the constraints, right? So if you have the 2 norm of ax less than or equal to b, then you are essentially penalizing the violation of the linear equality constraint ax less than or equal to, ax equals to b, right? So that kind of gives you a way of forcing this method to satisfy this equality constraint, okay? Yeah, and the other way to look at this problem is the following. We can rewrite the original problem as this problem here. Why this problem is equivalent as the original problem? Yeah, exactly right. So if you are adding this term to the objective function, right? But in any feasible solution to the original problem, this term is 0, right? So that's why even if you add this penalty term, it doesn't change the problem at all, right? Since any feasible solution satisfies this, okay? So then if you do the Lagrangian of this modified augmented problem, then you will basically recover this augmented Lagrangian function, right? So you are just bringing this to the objective by multiplying a dual multiplier. Okay, so now let's modify this problem a little bit, and modify the algorithm a little bit. Then we will come up with a method called method of multiplier, right? So the iterations of augmented Lagrangian is exactly the same as the dual ascent method, right? You are just first optimizing the primal variables while you fix the dual variable. Then you update the dual variable by the gradient of the dual function, right? Through a step size alpha k, right? So that's what we did in the subgradient method as well, right? You first solve a subproblem to optimize the primal variables, then you do a gradient ascent direction to the y variables. Okay, so now let's think about how we are going to choose the step size. Remember that in the previous lecture when we talk about subgradient methods, we were talking about the heuristics for choosing the step size mu, right? Here we have a more rigorous way of choosing the step size mu because in this lecture we assume the function is differentiable and the problem is convex. So we will show a more rigorous way of choosing the step size. So here's the intuition of choosing the step size. So since we know this is this is a convex problem, right? Then the KKT condition would be necessary and sufficient. So let's write down the KKT condition involves primal feasibility, right? So you have the primal constraints here, and stationarity is essentially the gradient of f plus a transpose y equals to 0, right? So those are the KKT conditions for the original problem. So the intuition here is that we want to choose alpha k such that we are close to satisfying the KKT conditions. Okay, so how we are going to do that? Let's assume at a given iteration we are optimizing this augmented Lagrangian function, right? So since this problem is convex, then if xk plus 1 minimize this augmented function, maybe I can write it out explicitly. This is kind of minimizing x f of x plus yk transpose ax minus b plus rho over 2 ax minus b. Okay, so this problem is apparently a convex problem, right? Because fx is a convex function, and this is like this is a linear term over x, and this is a quadratic function of x, right? The norm function is a convex function. So here, since you are optimizing over a convex function in the particular iteration, the necessary and sufficient condition is just the gradient over x is 0, right? So if you take the gradient of this function, I'm not going to do it, but you can believe me that the gradient of this function is this here. And then you set the gradient equals to 0, right? Okay. So the optimal xk plus 1 need to satisfy this constraint here, right? That's what this first order optimality condition gives us. But now the next step is we want to update the y in the next step, right? So here you can see that, let's compare these two terms right here, right? So here we know that this term is a gradient, but we just don't know what will be the good step size. Here, we know that the optimal xk plus 1 should satisfy this constraint here. But then we don't know how we are going to update y, right? So we already know yk. We want to know, what will be a good yk plus 1 for the next iteration of y. But here, as you can see, you can find a very good way of updating the y, because if you compare this condition with the stationarity condition, they have a very similar structure, right? So they are both the gradient of fx plus a transpose y. So if you update yk plus 1 to be this term, you will satisfy the stationarity condition. Okay, again, the optimal sk plus 1 have to satisfy this condition, right? But now you should think about how you are going to update the yk in the next step, right? So you are using the old yk here to get the xk plus 1. But now you are thinking about what should I do for the next iteration of y. But let's say if you set this term to yk plus 1, right? So let's say if this whole thing is your yk plus 1, then your xk plus 1 and yk plus 1 will satisfy the stationarity condition. Okay, right? Yeah, so you can check that. Then that is basically suggesting we should choose alpha, we should just set alpha k as rho, the penalty term, right? Since if this is yk plus 1, then then alpha k equals to rho, right? So that means choosing the step size to be the same as your penalty term is a good option, right? Because that satisfies your stationarity condition. Okay. So you can try to absorb this logic very slowly after the class. So then let's talk about a practical implementation of methods of multipliers. So one of the ways is that you solve those problems exactly at each iteration. But in practice, you don't have to solve it to optimality. You can just terminate when the gradient is less than or equal to a small number tau k here, and then you can gradually decrease tau k at each iteration. The other thing is that you can gradually increase the penalty term, right? So the larger the penalty term, the more likely you are going to satisfy those feasibility constraints. So that's why you can gradually update this penalty parameter by choosing the new iteration will be something larger than the rho in the previous iteration. Okay, so you can think about the penalty term as something to make your methods more stable. Yeah. Okay, so any high-level questions here? Okay, yeah. So then we've already talked about how to apply methods of multiplier for equality constraint. We also want to do inequality constraints, right? So we will show a very simple case where we have a linear inequality constraint. So this is essentially minimizing a convex function subject to linear inequality constraints. So from here, a naive way to do that is let's simplify the notation a little bit. We write C of x to be ax equals to b. And then, we can kind of convert this linear programming problem to the standard form, right? You add a slack variable s, and this is the constraint becomes cx equals to s, and the slack variable is s greater than or equal to 0. We just convert an LP to the standard form. And then the Lagrangian multiplier has to be greater than or equal to 0 because this is an inequality constraints. So here we wrote the augmented Lagrangian for this problem. We only dualize this equality constraint. We still leave the inequality constraint into the constraint, right? So then you can apply the techniques we already developed with the equality constraint to solve this problem. Okay. Right. So one of the things we first want to do is that we want to get rid of this inequality constraint, right? So if we don't have any inequality constraint, we already know what to do, right? When we have a linear equality constraint, we already know what to do. But then, how do we get rid of these slack variables? It can be done by a very simple analysis of this augmented Lagrangian problem. Okay, so here, as you can see, for a fixed y, right? Remember, in each iteration, you are first optimizing the primal variables for a fixed dual variable, then you update the dual variable according to the gradient, right? So for a fixed dual variable, what are the optimal primal variable you can get, right? Since this problem is clearly a convex problem because you have some quadratic terms with respect to some linear functions, right? The C of x is a linear function. S is, of course, it is a linear function. So according to the operations that preserve convexity, you can show very quickly that this function is convex with respect to both x and s. And then the optimality condition would be the gradient of, if this is unconstrained, then it is like the gradient of x equals to 0, the gradient of s equals to 0. But we do have this constraint s greater than or equal to 0, so it's not as trivial. Okay, so maybe let's first find out how to find the optimal solution of s. So we can rewrite this problem. Maybe people are not so comfortable with vectors and so forth. We can write this problem in a scalar form, right? So let's rewrite the augmented Lagrangian function in a scalar form. So that will be f of x minus summation of let's index the constraint as ci of x, right? So let's assume we have a I constraint. That will be ci of x equals to si for all I from 1 to n, right? So now we are kind of explicitly writing out all the constraints instead of writing the constraint in a matrix form. So then those constraints will be sum over I, yi, ci of x minus si, right? Okay, so that from 1 to m. Okay, then let's take a look at this norm. That will be rho over 2. Since we are doing this for each constraint, that will be I from m1 to m ci of x minus si squared. Right? That's a definition of 2 norm. Okay. So the definition is this clear here? Yes.
So C of x equal to x minus b. Do I have that right?
Yeah. So C of x equals to ax minus. You can think about a Ci of x as the first row of this linear constraint. Right. So each of the Ci of x represent one single linear constraint. Okay. So that basically you can write it out as this form. Okay. So now as you can see that this problem is separable for all the s variables, right? So each of the s, each of these si variable is separable, right? The si does not have nothing to do all the other slack variables, right? Each of these is a summation and they are separable. Okay, so when you try to optimize this function, it is a convex function with respect to Si, right? So then each of the Si can be optimized separately, right? Then we know that at the optimal solution, okay, let me try to find some place. Maybe, yeah, so the partial derivative, if this problem is unconstrained, right? Then the partial derivative of this function L, the augmented Lagrangian function with respect to Si should be equals to 0, right? The gradient with respect to Si equals to 0. But this problem is not unconstrained because S is greater than equal to 0, right? So let's maybe gather the terms related to all the Si variables, right? So the terms related to the Si variables are the following, which is yi times Cix minus Si plus rho over 2 Ci of x minus Si, right? Since they are separable, I'm just gathering the terms that involve the Si variable. I'm not doing anything else. Okay. So what is this function with respect to Si? What type of function is this? It only has a single variable, right? If you only consider this as a function, this as a function of Si, it only has a single variable, Si, right? And then this is a quadratic function, right? So the function looks something. It's very simple. You have learned it in middle school, right? This function looks something like this, right? It's a single variable quadratic function, and rho is greater than or equal to 0. It's some function like this, right? So we know that for a quadratic function, you do know how to find the minimum of a quadratic function, right? You have studied that in high school. There is a formula. You can do that, right? So actually, you can take the partial derivative of this with respect to Si and set it to equal to 0, right? That will be yi minus yi. So what will be this plus rho times, maybe it should be minus, right? So minus rho times Ci of x minus Si. I don't know, did I take the derivative correctly? Yeah. Okay, so then you know that if it is unconstrained, this is a minimum point for you solve this problem. The minimum point is obtained at the solution to this problem. Okay, so now you have the minimum point, which is a solution to this equation. You don't know if the minimum is obtained at greater than or equal to 0 or less than or equal to 0, right? So if so let's say if the origin is here, this is 0, then the minimum can be obtained here, right? Because the minimum of this quadratic function is greater than or equal to 0. However, if you have the other case, let's say you have the minimum here, but 0 is here, right? Then the minimum of this function is obtained at x equals to 0, right? Because you have the s is greater than or equal to 0, you cannot obtain the minimum at x less than or equal to 0. Then the minimum is just x equal to 0. Okay, and this is a very simple thing. Yeah, so basically summarize what I have said. When you set the gradient with respect to s equals to 0, then the solution is this term here. But you don't know if this term is smaller than 0 or greater than or equal to 0. But at least you know that it is either 0 or if this is greater than 0, we take this term. If it is less than or equal to 0, you take 0 here, right? And then you can just plug in this the optimal solution of S into the formula, right? There are two cases. If this minimum is less than or equal to 0, then you can rewrite this term as here. I'm not going to do the algebra here in class. You can double check if this is correct. Okay, so now with that you can get rid of the slack variables, right? Because you already know what are the optimal value of slack variables for any given x. But the x is unconstrained, then you can use the previous method to solve this problem here. And similarly, you can update the dual variable using what we have discussed before. Okay, any doubts here? I'm not going to the details of the algebra here. Okay. Yeah, so we can talk a little bit about the convergence of this method, but not giving the proof of that. For convex problem, this method will converge to a primal feasible solution, right? So that's a key difference from dual ascent. In dual ascent, you are not guaranteed to recover a primal feasible solution, but with this augmented term, you can think about it penalize a violation of the constraints as well. Then the primal residual will converge to zero, give you the optimal solution. Okay. But this type of method also comes at a cost, because when you add the penalty term, you may destroy the structure of the original problem. Okay, so what I mean is that when you are doing Lagrangian decomposition, then let's say you dualize the complicating constraints. Right? So maybe let me show that real quickly. So recall that in what we have is something like C transpose X subject to some constraints of X, some constraints of let's do it very simply, like C transpose X plus D transpose Y. And then, this should be probably, we'll just also do C transpose Y. Y has to satisfy some constraint, then you have some another complicating constraint, Y equals to Y, X equals to Y, right? So now if you dualize this constraint, this complicating constraint, that will be, the problem will become separable, right? You multiply this by a term nu. So this is the X problem, then you have a Y problem as well. Okay, so this is what we did in Lagrangian decomposition, right? After you dualize these complicating constraints, then the problem is separable, right? But if you add an augmented term, what is going to happen is that, the Lagrangian function with an augmented term will be the following: will be C transpose X plus C transpose Y plus mu times X minus Y. But then you need to have a term 2 over rho plus basically since maybe still write it in vector form. Okay. So recall that in augmented Lagrangian, you are going to penalize the constraints you dualized, right? Okay, but this term is very nasty because it involves both X and Y variables now, right? You cannot separate the problem anymore if you have an augmented term. Right? Think about if you these X and Y are both one dimension, at least you have a term X times Y, right? So then the problem is no longer separable. This is not nice, right? We do want to protect the structure of the separable problem. Okay, so how do we resolve this issue of augmented Lagrangian? So then that comes to the final thing we will talk about here. It is a method called alternating direction methods of multiplier, ADMM. It is a quite popular method nowadays, especially with applications in machine learning nowadays. A lot of people use this type of method to solve problems. So the nice thing about ADMM is that it is an augmented Lagrangian method, but it also protects the structure of the decomposable structure of the problem. Okay, so now let's say we look at this problem with some sort of decomposable structure, right? You have f of x and h of z. They are decomposable, but then you have these complicating constraints here, right? And now if you write the augmented Lagrangian, and then you naively apply methods of multiplier to the augmented Lagrangian, then x and z are coupled, right? You cannot decompose them. But in ADMM, what they do is that they are going to minimize x and z separately and sequentially. Right? So when you minimize x, you fix z and y at the value from their previous iteration. Okay, so then you can separate x and y, x and z variables, right? So first you fix zk, yk, and then you optimize for x, and then you fix xk. Of course, here xk is updated to the next iteration, xk plus 1, and you fix yk as well, and you just optimize for z. Okay, and then finally, after x and z are optimized, then you can take the gradient step for the y variable. Okay, so what are the difference of this method compared with augmented Lagrangian? You have some idea? No? Okay. So maybe the other way to ask is that, what if you apply methods of multiplier or augmented Lagrangian to this problem? What are the two iterations of this problem? You first optimize a primal variable, then you optimize a dual, right? Okay, so what are the difference of the methods of multiplier compared with this one here?
That we optimize separately and sequentially.
Yeah, can you be more explicit?
In what sense?
Okay, I think you are already very clear. Okay, yeah. So in the methods of multiplier, recall that you have two steps, right? So maybe let's go back a little bit. Right. So you first optimize a variable involved in this augmented function. Then you update the multiplier. So it only has two steps. You are solving only solving one optimization problem and take a gradient descent. Right. So what is the difference of this compared with the other? So you optimize twice, right? So in other words, if you apply methods of multiplier to this problem, in this step, what you would do is that you optimize x and z simultaneously, right? So that will be L row x, z, yk, right? So that's what you will do when you use methods of multiplier, right? You fix the dual problem, then you optimize a primal variable, right? And then you update the dual variable by taking a gradient ascent step. But in alternating direction methods of multiplier, you want to optimize x and y sequentially instead of doing this step simultaneously, right? If you want to do it sequentially, you have to fix the zk variable when you're optimizing x, and then you have to fix the x variable when you optimize z, right? Okay. And this will make the problem decomposable, since you are fixing the rest of the variable when you optimize one of them. Yes.
Does the order matter?
Does the order matter? That's a good point. I don't know. Maybe the convergence are not affected by that, but computationally, I guess it will be different. That's just my guess. Yeah. Okay. So this is like the alternating direction method multiplier is similar to something called coordinate descent. Right. For example, when we are doing gradient descent, we are taking the gradient of all the variables in this problem. Right. But coordinate descent meaning that, let's say if I optimize each variable separately, right, sequentially maybe. Let's say if I have two variables, I first fix x2 and just find the optimal value of x1. Then I fix x1 and then optimize for x2. Right? This is something called coordinate descent or block coordinate descent. Right? So here you can think about x and z as two blocks of variables. I'm not doing optimization on x and z simultaneously. What I do is that I first optimize x, then I fix x and optimize z. Then I go back to optimize x. Right? So there's something called block coordinate descent. It also has to do with a dual variable. Right? So this is called ADMM. So here the features is that we are doing one cycle of block coordinate descent in x and z. The minimization over x and z only add a quadratic term to it respectively. Okay. And then that still maintains the decomposable structure of the problem. And of course, in each of these iterations, you can add some additional constraints that are related to z and x separately. They are still decomposable. Okay, so it has very, very wide applications to federated learning. It is a concept where when you are training a machine learning model, you train it on different data owned by different users, right? So for example, each hospital may have some data related to the patients, but you don't want to share the data of those patients, right? So that's why you can have a distributed methods to train a machine learning model based on the data owned by different hospitals, right? You have a postdoc in our department working on this type of application. So the most common algorithm to solve federated learning is the ADMM type of methods. Okay. And there are methods related to other applications like image processing and so forth. Okay, so then we can also decide what will be the good step size for updating the dual variable. It's similarly to what we did in the methods of multiplier. You can write down the KKT conditions of those problems, and you will find out that to satisfy the KKT conditions, you should choose the step size as the same parameter as the penalty term. That is a good step size to choose. Yes?
So, if one of the variables reaches convergence, like the minimum value, does it guarantee that the other variable also will reach the minimum at that fixed value?
If one of the primal variable obtains optimality, does that guarantee optimality?
Yeah.
Okay, yeah, that's actually it's not so easy to check, right? You don't know the optimal value is, so that is related to the convergence of ADMM. I will show that in the next slide, actually.
But in general, how do you decide the convergence?
Yeah. So I will show it in the next slide. Okay, yeah. Yeah. So when you decide convergence, first of all, one of the things you can decide is the residual goes to 0. That means that it satisfies primal feasibility. Right. The other thing you can get is from the ADMM, you will be able to get a dual solution of the original problem. Right. Then it's similar to the dual decomposition, you get the lower bound. And if it satisfies primal feasibility and the primal objective converge to the dual objective, then you get convergence. But then that requires some assumptions for the convergence. We won't cover the details of why it converges, but you can implement this and check those convergence properties. Computationally, it's easy to check convergence, but proving convergence is very complicated. Yeah, so also you can apply ADMM to problem with decomposable structure. So here just show, people call it consensus optimization. If you have problem with decomposable structure, let's say if the objective function is decomposable, then you can create, just like what you did in the Lagrangian decomposition, you can create a variable z and set xi equals to z, right? That doesn't change the problem. It should be for all I from 1 to n. Okay. Yeah, and z is a global variable, right? Okay, so this is very similar to the case where we are doing two-stage stochastic programming, right? You can reformulate the problem such that you create a duplicate for each of the first-stage decisions, and you set it to the variable in the first scenario. So here it's like you create a z variable and set all the xi's equals to z, right? And then we can apply ADMM by dualizing those complicating constraints and add a penalty term to the complicating constraints. And now you solve each of the xi separately by this augmented Lagrangian type of problem. So this is nothing but an application of ADMM to when you want to decompose the problem by its structure. Yeah, so there are a lot of algorithms similar to ADMM, and there is some rich literature of the history related to the ADMM, which we will not go to the details, but you can keep those references. So I want to leave a final comment on how to apply augmented Lagrangian and ADMM for MLP problem. It is not very mature. As you can see, the three references I gave here are all very recent. It is still under development here. Maybe this paper, they can prove convergence of some sort of ADMM methods on mixed integer linear programs, but that can be very expensive to do. Okay. So if you are curious, you can check those papers. And then all the references you can find are here. There is a tutorial by Stephen Boyd on ADMM method, and then the augmented Lagrangian is from this numerical optimization book. Also we have there is a tutorial by Stephen Wright, who is author of the numerical optimization book. You can check these lecture notes as well.